All right, guys, so we're going to start our video review here for today. So this is for 16-1. So we will be going through and talking a lot about all the different heat change calculations that we have looked at as we have gone through and discussed previously. So the first thing to keep in mind before we start talking about all this is understand the difference between system and surroundings, because when we talk about thermodynamics, we are talking about the transfer of heat from one thing to another. Well, how do we define that one thing to another? Because energy transfers in so many different ways. So we have to be able to define what we're looking at versus what we're not looking at. And so the system is what we are looking at. System is what we're looking at, and your surroundings is basically everything else. And how we define that is up to us, but it really makes it easier because we have a specific fine line of what we're looking at versus what we're not, so we can see and calculate the energy change much better than if we have to take in all the different variables. Because, you know, if let's say my hand is touching a desk, well, there's a lot that's going on there. There's energy that's probably flowing, heat that's probably flowing from my hand to the desk. There's also air that has come in contact with the desk that may have energy in it that flows into the desk or out of the desk depending upon the temperature of the room. There may be some sunlight that comes into the room. That light energy plays a role in this. So it's really important that we define specifically what we're looking at versus what we are not looking at. And that makes these energy calculations a lot easier to digest. We also want to make sure that we take a look at endo versus exothermic reactions. Remember, this is energy going in. And exothermic energy goes out. Remember that if energy goes in, we break bonds. And when energy goes out, we make bonds. And we've talked about that previously, but it always requires energy in some way, shape, or form to break a bond. So the breaking of bonds is an endothermic process, whereas the making of bonds is an exothermic process. So let's talk a little bit about some of the different laws of thermodynamics. And I don't want to get into too much detail about the different laws of thermodynamics. The first one basically just says that energy cannot be created or destroyed. Energy cannot be created or destroyed. So what does that mean? That means that energy is finite in the universe, and that all chemical processes, all processes that involve the transfer of energy, none of it ever just disappears. Some of it may get lost to the environment, but it still exists. It just exists in a different form. So we cannot create energy, nor can we destroy it. Second is that entropy, remember entropy is disorder. Is always increasing. Things tend to want to go to a state of disorder. We've talked about that as well when we talked about our room. In a room or in a house, things tend to naturally go to disorder. You have to put energy into it to make it nice and clean. It's the same concept with the concepts of the universe. Things tend to want to go to a state of disorder or a higher state of entropy. And then third is that there is no molecular movement at absolute zero. Basically, that just simply says that temperature is a measure of kinetic energy. The higher the temperature, the more kinetic energy and the more movement you see in those molecules. When the temperature is an absolute zero, that is when no molecular movement can exist. So those are your three basic laws of thermodynamics again. So another thing to keep in mind here, make sure you do know that temperature is a direct measure of kinetic energy. It is not heat. Okay? That specifically is your change in kinetic energy. That is the transfer of energy from one thing to another is heat. So when I take the temperature of something, I'm not measuring heat, I'm measuring the kinetic energy. When I look at the change of kinetic energy or how that has changed over time, that can be referred to as heat, and the unit is joule for that. Now, again, we have the ability to calculate that using this equation, Q equals mc delta T, where Q is energy, M is mass. C is specific heat. T final is your TF, sorry, is your final temp. And TI is your initial. And we can just simply plug those numbers in and solve for any one of the variables that are there. We'll give you 4, and you can solve for the 5th. It's pretty straightforward on how to do that. Now, interestingly enough, the specific heat, what is truly specific heat? Specific heat is how many joules are required to raise 1 gram of the substance 1 degree Celsius. And this chart here kind of puts it in perspective of how well something absorbs heat without changing temperature. Basically, how good of an insulator is it? And if we look at liquid water there, it has a specific heat of 4.18 joules per gram, joules over gram degree Celsius, meaning it takes 4 joules to raise 1 gram of that substance 1 degree Celsius. If I look at some of the other things down there, like iron has almost 1/10 the specific heat. So if I added 4 joules of energy to liquid water, it will 1 gram of liquid water, it would raise 1 degree Celsius. If I did the same for iron, it's going to raise almost 10 because the specific heat is 10 times less than that of liquid water. So as a result, iron, when it absorbs heat, the temperature raises at a much faster rate than what it would with liquid water. Liquid water is a better insulator and it absorbs the heat, resisting the change in temperature better than the ones down near the bottom. So let's go ahead and analyze one of these problems here. How many joules of heat are required to raise the temperature of 550 grams of water from 12 to 18 degrees Celsius? So we plug those numbers in. So we want to know Q. We want to know Q. We're given M. C is given in our chart, which is nice. And we're given our initial and our final temperature. So we just solve. So Q equals M. C, which is specific heat of water, because we're looking at water here. And final minus initial. And then all we do now is we just plug this into our calculator and very easily solve for the answer. And you are going to get relatively large numbers here. A lot of times we'd put these into kilojoules, but I'm not a huge stickler on that at the moment. So this is 13,794 joules. So a lot of energy going into that in order to be able to get your answer there. Okay? Pretty straightforward on how to do that. So just read these questions very carefully, and you guys should have no problem with that. Let's keep going with the next practice problem here. It says find the mass of a sample of water if its temperature dropped 24.8 degrees Celsius when it lost this much heat. So we were given a little bit more information here. We're not given a final and initial, but we are told the change in temperature, right? If the temperature dropped 24.8 degrees, that means we had a higher initial than final, right? Because the temperature went down. So we lose 870 joules of heat. So that means that joules is a negative value. We want to know the mass of water. Remember, it's water, so we use the same specific heat value. And then delta T, it dropped this much, so we're going to use negative 24.8. Because again, the temperature decreased. And now we just algebraically solve for M. And what we get for our mass is 8.4 grams. Okay. So again, very easy to just plug in and solve, but make sure you read those questions very carefully. Now, remember, we've talked about this a lot with our previous units, is that phase changes require energy as well. We've looked at this diagram a lot, where here you've got solid, liquid, gas, and in between here are your phase changes. So we have energy down here at the bottom, temperature on the left-hand side. What this graph tells us is that energy is required for a phase change to happen, even though the temperature does not change. Now, because the temperature does not change, that would make it very difficult to use Q equals MC delta T because you would never see a change in temperature. So as a result of this, we have to come up with a new equation. Q equals HF times M. Again, Q is energy in joules. HF or HV stands for heat of fusion or heat of vaporization. You'd use heat of fusion if you're going from solid to liquid state or the opposite way. and vaporization if you were going from liquid to gas. And M, again, is just your mass in grams. So now we can do a couple more different problems with this. So let's take a look and see what we got going on here. First thing, heat of fusion for water at 0 degrees is 334 joules per gram. And we get heat of vaporization as well. So it says how much energy is released when 20 grams of water is frozen. Okay, so we're going to start, because we're at 0 degrees, notice there's just a phase change here. There is no change in temperature. So we're going to use that previous equation, Q equals HF times M. And we just simply plug in our numbers. HF is 334 joules per gram, and our mass is 20. So we can solve for that pretty easily. We're just going to take 334, and we're going to multiply it by 20. And our Q value for that is going to be 6,680 joules. Okay, pretty straightforward on how to do that. Bottom one here says determine the amount of heat in joules required to raise the temperature of 50 grams of ice from negative 20 degrees Celsius to 40. So this is where this gets tricky. Because if you remember on that chart, great chart here, this part here, when we go undergo a phase change, requires a different calculation. What the question is saying is we need to go from negative 20 degrees of water down here to 40 degrees up here. So that's going to require 3 different calculations. One calculation is to go from negative 20 degrees Celsius to 0. The next one is going to require us to go from 0 degrees Celsius of ice to 0 degrees Celsius of liquid water. And then the last one, we're going to go from 0 40 degrees Celsius. So we're going to do 3 separate problems here. Anytime you see a change in temperature, we'll use Q equals MC delta T. If the temperature stays constant, we'll use Q equals HF times M. So do the first part here, Q equals 50 grams, so M. C, the value of C for ice is 2.11. And then our final, which is 0, minus our initial, negative 20. Here, kind of the same concept, but this is our phase change. So we're going to use Q equals M times HF. And then the last one, Q equals MC delta T again. But remember, the C value changes because we're going from, we're using liquid water instead of ice. And then we just solve for all 3 of those Q values. So first one is 2,110. We're going to add that to 16,700 joules. And we're going to add that to 10,450 joules. We add all those together to get a grand total of 29,260 joules. Okay. Folks, that's really all there is to it. Just make sure that the tricky part here is this bottom question here. Make sure you understand that if there's a phase change in the middle of this, you got 3 separate problems you have to do. One to get to the phase change, the second to make the phase change happen, and then the third to go beyond the phase change. Also be aware that specific heats of different things in different states of matter may be different as well. All right? Hope you guys have a great day. Make sure you like and subscribe, and we'll talk to you later. Okay? Have a great day, guys. We'll see you soon. Bye-bye.